Welcome everyone to today's Juice webinar, organized in collaboration with Europlanet and ESA. Today we have two excellent speakers for you from close to the Juice project and close to Europlanet. The first speaker will be Olivier Witasse from ESA, and Olivier will present the current status of the Juice mission. Olivier is the project scientist for the Juice mission at ESA since 2015. He holds a PhD from the University of Grenoble in 2000, and his background is in the study of planetary upper atmospheres. Olivier has been with the European Space Agency since 2003, working on many projects, which included Huygens, Mars Express, and now Juice. Our second speaker today is Michel Blanc, and it's a very special speaker. Michel is at the origin of Juice in a way, because in the early 2000s, ESA started talks with NASA at a high level for a joint effort to study the jovian system, and Michel was leading that effort from the science community side. Those efforts initially led to the Laplace mission proposal to ESA, and that proposal eventually led to what is now Juice. So in addition to that, Michel was also part of the core group of people at the origin of Europlanet itself, together with Olivier. That also happened in the same time period, right, in the early 2000s. So I'm really happy to have both Olivier and Michel here today. Michel, he is a space plasma physicist and planetary scientist, currently an emeritus professor working at IRAP in Toulouse, France. His research focuses on the coupled magnetosphere, ionosphere, thermosphere systems of Earth and the giant planets, and on comparative studies of planetary systems. He has been interdisciplinary scientist on the Cassini-Huygens mission. His current interests focus on Jupiter system. He closely follows Juice, of course, and at the same time is a co-investigator on NASA's Juno mission. Michel is a member of the Air and Space Academy, of the International Academy of Astronautics, and of the Academy Europaea. And of course, he is part of Europlanet Society. He also chairs the panel on exploration of COSPAR. Juice has been in space for slightly over 2 years now. The next stop is Venus. So let's hear about the status of Juice first. And without further ado, Olivier, the floor is yours.
Good morning, everybody, or good afternoon. This is a very short introduction because the main topic of today is the talk of Michel, of course. So a short status update on the Juice mission. Juice means Jupiter Icy Moon Explorer. And as Martin mentioned, this month we celebrate the 2 years in space. It's always good, nice, and emotional to remember what happened 2 years ago. It's one of my favorite images of the Juice launch. We have a long cruise ahead of us, and we still have to be patient because we still need to wait for 6 years before arriving at destination. We're also quite happy to have been joined in space with our colleague spacecraft, which is called Europa Clipper. It was launched last year, and now we have 2 spacecraft en route to the Jupiter system, and we are very complementary because Europa Clipper will focus on Europa, and we'll focus on the other moons and Jupiter. And we have set up a working group, including scientists from both science teams, to work together to make sure we have the best science return with 2 spacecraft at the same time in the Jupiter system, which is, I think, very great. Just to remind you about the timeline, Juice is a long project. We have to be patient when we work in planetary mission. Everything started around 2007, and the mission will last until 2035. So 2037, we need to check for the extension. It's too early to talk about that. And basically, we have 4 blocks. The first for 7 years of mission, call for proposal, studies, selection of mission and payload. Then we had 8 years of development phase where we build the spacecraft, the instrument, put everything together, test which everything is okay, preparing for the launch campaign. The launch 2 years ago, and then 8 years of cruise because it takes time to go to Jupiter. Juice is a very heavy spacecraft. And then we are waiting for the final phase, which will be the best one, of course, for the scientific community to get all the harvest of everything that we are preparing now. Just a quick recap on the JUICE science objective. So we have two main topics. We want to study whether the high sea moons of Jupiter, so Europa, Ganymede, and Callisto, how they can be characterized in terms of habitable worlds. In other words, do we have a planetary object we can maybe host life or have at least have the conditions for life? And why do we have such a condition around a planet like Jupiter? And the main investigation here will be to study the Ganymede moon, in particular the interior and the presence of the subsurface ocean. But we want to study this moon in isolation. If you want to understand the properties of this moon, you have to study the jovian system as a whole, and in particular the Jupiter atmosphere, the magnetosphere, all the other moons, the ring system, and all the connection between those bodies. And that will be the main topic of the talk of Michel, the couplings between all parts of this very interesting system. We are not doing only planetary science, because Jupiter is also a model or an archetype for exoplanet. So there will be a very interesting link. We have not yet started to explore too much, but that will come in the coming years, to explore the link between what we learn from Jupiter and its system, and how it will be interesting for the exoplanet community. Just also to put things into context, of course, I'm mainly interested in JUICE as project scientist, but just to tell you that we have many other missions, either in legacy phase in the bottom line here, so from Ulysse to Cassini-Huygens, so you can find the data into the archive. We have many missions in operation, from Solar Orbiter to JUICE as a function of the distance to the sun. And so also active mission, a lot of data into the archive, and some mission into preparation. So JUICE is only one part of the full solar system exploration by the European Space Agency. If you want to get more information, more detailed information on the JUICE mission, we have set up a special collection of articles in Space Science Review. So it's relatively easy to find the link on the web. And we have many papers on the trajectory, on the ground segment, and on the instrument. And hopefully the collection will be soon terminated by the end of the year, so you will get all the information. But I really recommend, if you want to get all the details, the science objective, to go find all these interesting articles. Talking about the cruise phase, so this diagram shows the cruise phase from the launch to the arrival at Jupiter, so 8 years, and on the y-axis you have the distance to the sun and to the Earth. So you see that we are approach the 25% of the cruise phase. The yellowish part means that we are relatively close to the sun, so we need to be careful with the thermal constraint. When we are in the white part, that means we are fine in terms of thermal design and pointing constraint. And you can see that most of the part of the cruise phase, we are still around the Earth or around the sun, and then from 2029, we'll finally go to Jupiter and reach Jupiter in 2031. The right plot is a little bit complex, but that's the amount of propellant that we'll spend in the cruise phase as a function of the day in the launch window 2 years ago. And basically the message here is that we have launched in the middle of the launch window, which is much better in terms of usage of propellant, because we could save some propellant later for the best scientific return. So that's one good point. And the second message of this plot is that we launched before the 18th of April. So that means last year we could have the moon flyby in addition to the Earth flyby. If we would have launched a few days later, it would have not been possible. So it's the celestial mechanics is always a very complex topic. So where is JUICE now? We are in our second orbit around the sun. JUICE is here. So we passed Earth last August. And we are towards an orbit which goes closer to the sun, as you can see here, close the orbit of Venus. And in fact, the next step will be the Venus gravity assist flyby in August. So that will be at that time, August 2025, we'll reach the orbit of Venus. And we'll fly by Venus at around 5,000 kilometers. And because we already got a lot of questions about what science and images we are going to get during the flyby, due to thermal constraints, we need to point the high-gain antenna always towards the sun. So we are very limited in terms of communication and data rate. So that means we have decided not to make any scientific measurement, not images for this one. For this flybys, the priority is really the navigation, which is the most important aspect of those flyby to go to Jupiter safely. So I will stop here and give the floor to Michel to tell us about all the mysteries of the Jupiter system and these fascinating couplings.
So good morning, everybody. Good morning, Europe. Actually, I'm in Beijing today, so good afternoon for some. It's a great pleasure, of course, to talk about the Jupiter system since I devote with our team at Europe a lot of time on it. It's a fascinating world, as Olivier explained, and well worth the beautiful journey that JUICE invites us to. So today I'll try to make a short summary of actually one of the themes of the JUICE mission, as Olivier said, understanding the Jupiter system as a template of a gas giant system. And for that, I want to say that, of course, coupling processes are really multidisciplinary theme, because we have to study not only electrodynamic processes that govern the magnetosphere, for instance, but also gravitation, radiation. So I'm working on that with a group of colleagues whom I would like to recognize first, who are the experts on the areas which I don't know about. So Valérie Lenné at Observatoire de Paris, of course, a great astrometrist who knows everything about tidal interactions. Ingo Müller-Wodarg at Imperial College, who models the thermosphere dynamics and the energetics. Alessandro Moura, who is deeply involved into the study of Io and the other moons and their interactions, and also Katrina Chapman, whom I would like to thank very much for her broad view of the Jupiter system and the data that feed our understanding of Jupiter system. So a lot of what I'm saying is theirs, and I wanted to thank them first. So let's go through, well, the Jupiter system is actually a complex system, which is also a multi-scale system. And so I will start by just describing what is the system and what are the objects in the system. So if we go from the large scales to the small scales, you will see that we are encompassing about a factor 10 to the 4 in the system. So first, you can understand the Jupiter system at the scale of the solar system, because the Jupiter Sun system, as you see it here, it's a binary system in a way, which has secondary potential wells on either side of the Jupiter's orbit, 60 degrees behind and ahead of it, where there are stable orbits for small bodies that we call the Trojans. So in a way, the Trojans that orbit the L4 and L5 Lagrangian points, there are thousands of objects, or probably more, which we don't know about, but which in a way are part of the Jupiter system. And they are so interesting. They tell us something about the history of the formation of the system, of course. They have a connection with the building blocks of Jupiter's core, probably, and of the moons, that it is really well worth going there. And actually, a NASA mission, Lucy, is on its way to these objects and will fly by, I think, 6 or 7 of them. For the first time, we have images of this object, and of course, we are looking forward very much to these new discoveries. Then, if we go into now the main potential well of Jupiter, so let's say inside the Hill radius, the first thing you find is a large group of, again, small bodies, the irregular satellites of Jupiter. I think we know between 100 and 200, but it's really a question of detection capability, because we detect more and more as the telescopes are improving their sensitivity. So they are orbiting on the edges, sort of the Hill sphere, at long distances from Jupiter. They are on highly inclined orbits, and more than half of them are actually on retrograde orbits. Just as the Trojans, in fact, these objects have never been imaged, even though they are also part of the story of the assembly of the Jupiter system. And I hope that one of the upcoming missions to Jupiter, maybe 2004, I don't know, we have the capacity of flying by one of these objects or several, because they are very mysterious and they are connected to Jupiter. Then we go inside the potential world, this time really deep, and of course we discover the most famous, the most popular, I would say, of the objects within the Jupiter system, which are the Galilean moons. You see there are 3 of them, Io, Europa, and Ganymede, and Callisto is out of this little screen, but it is also, of course, very important. And we will see they play a very important role because of the Laplace resonance. So you see we have moved from 750 million kilometers to now 50 and 3. And in the next step, we dipped very close to Jupiter. And very close to Jupiter, well, we discover the rings. Jupiter has very small, tiny dust rings, which are coupled to 4 tiny irregular moons, which are really deep inside Jupiter. And we believe that actually the dust rings is just generated by the impacts of meteorites on the surface of these tiny moons. Also, a very fascinating small system of rings, which is unique compared to all the others, which Juno is going to study in detail, in fact, in its extended mission. So finally, of course, I should not forget my favorite object, which is the magnetosphere. And the magnetosphere, in fact, is actually covering a large fraction of the system. And as you see, and as was shown previously by Olivier, it's really a place for interactions. There is a giant magnetodisk, which is basically generated by the outward expansion of the Io torus. There are specific electrodynamic interactions between each of the moons and the Jovian magnetic field. So I will come to that, and it's a good introduction to the subject of interactions. But all these are, let's say, radiation interaction and electrodynamic interactions. But interactions are not just electrodynamic, and of course, gravity is in fact the most important aspect of the interaction. And now I'm going to move to this description of a collection of objects to a description of the interactions between the objects. So that's the subject of the next slide here, where you see that we have tried to summarize what are the interactions inside the system. So we can define the Jupiter system, if you want to describe it as a system, as a set of different components. So let's say the component 1, C1, it's Jupiter itself. Most of the energy in Jupiter is inside Jupiter, in fact, and all the rest is driven by it. Then the second object is Io, and Io is in a way the energy converter of this system. It receives tidal heating from Jupiter via the tidal interactions, and with that it generates the torus, and the torus drives the magnetosphere. So it's a sort of energy converter between gravitational energy and electrodynamic energy. The interaction of Io with the magnetosphere generates, well, the magnetosphere and magnetodisk. Most of the plasma at Jupiter, not all, but most of the plasma comes from the Io torus. So this giant flywheel, which is the magnetodisk, is the fourth component here. And of course, we should not forget that along the transport of plasma in the magnetodisk and in the motion of the magnetic field, there is an interaction every time different with each of the icy moons. So Europa, Ganymede, and Callisto, they all interact with the magnetosphere at the same time as they have tidal interactions with Jupiter. And let's not forget on the left that, of course, everything is embedded into interplanetary space and receives energy from the sun. So you see here, we summarize the interaction. Let's say that in green, we have the tidal or gravitational interactions, the coupling between Jupiter and its moon, and also a gravitational coupling of Jupiter to the sun, of course. At the top in red, we have the electrodynamic coupling. So it goes through the magnetosphere and the plasma interactions. So in red. And in dotted blue, you have here, of course, the radiation and bombardment processes, which include the solar wind, which include solar irradiation. and which includes the radiation of each of these bodies. So if you really want to understand the Jupiter system as a system, well, you have to understand what are the fluxes of mass, momentum, energy between these 5 components, and what are the mechanisms that mediate these transfers of mass, momentum, and energy. So in this short talk, I will try to briefly go to invite you to a walk through the system. So we will start with Jupiter itself and to see what Jupiter generates to interact with its environment. Then we will move to Io. We will describe the interactions of Io and the elements with the magnetosphere. And finally, we'll move to the magnetodisk and back to Jupiter to close the loop. So that's the plan. So let's start with Jupiter. So Jupiter's, of course, interior. It's something which had really, it's a place where Juno, so the current mission orbiting Jupiter, has really revolutionized our view of what's inside Jupiter. Before Juno, the core accretion model of the formation of Jupiter was such that we really believe that a well-formed Jupiter had to have a sharply defined core. So basically a big sort of terrestrial planet made of ice and rocks, around which, thanks to its gravity, enough gas had accreted by runaway accretion during the formation of Jupiter and of the solar system as a whole. So we were expecting a well-defined core with an envelope of hydrogen. And well, thanks to, in particular, the gravity experiment on Juno, we were able to find that, in fact, there is not a sharply defined core, but more a dilute core, and that the transition between the core and the mantle is continuous. Juno has also made a lot of investigations into, let's say, the interface between the mantle and the atmosphere. Also determine the place where the dynamo, which generates the magnetic field, takes place. So it's about here, at about 80% of the radius of Jupiter, so relatively close to the surface, where there is already a layer of metallic hydrogen, which is capable by its motion to generate a magnetic field. And there is even some processes of chemical separation, so a rain down of helium inside hydrogen at some depths into the interior of Jupiter. So as I said, the magnetic field is a result of the internal dynamics of Jupiter. And let me show you here what Juno found. In fact, thanks to the orbits of Juno, which come very close to the planet, it is possible to determine the decomposition of the jovian magnetic field into its harmonic expansion to a very high degree, and to give a very good determination of the surface distribution of the magnetic flux coming out of Jupiter. So you see that this is a very non-dipole field. And as you can see here, actually, it's a very strange system where you see there is actually about twice more magnetic flux coming out of the North Pole than out of the South Pole. And there is even a sort of big anomaly near the equator. So some of the magnetic field lines will come out of the North Polar regions, instead of going to the South Polar regions, are connected near the equator to this big, what we call the blue spot here. So highly non-dipole magnetic field generated inside. The reason for the non-dipole structure is the fact that actually the dynamo layer is close to the surface. So the high-level non-dipole components remain very important. And even more so, what is very interesting when you look at this, what we call this blue spot, this gigantic anomaly, which is right at the equator, is that with Juno, and actually in consistency with what Galileo had been finding before, we can find over the years that this blue spot is moving with time. And in fact, it is moving by a fraction of a meter per second. So we know directly just by the observations that the dynamo-magnetic field of Jupiter is not static. It has a very large secular variation, and it tells us that it is very important, of course, to understand how this magnetic field is moving with time, because we see it moving over decades or even over years. But of course, it's been moving with time over millions and billions of years since the formation of Jupiter. So it is very important to understand that, because the magnetic field, of course, is what is going to control the structure of the magnetosphere. The magnetic field coming out of Jupiter is pervading the whole outer space, and it is going to control all the plasma transport processes outside. Well, now, what are the plasma sources? Of course, the plasma sources are related to the moons themselves. So I'm going to move now from the interior of Jupiter to the moons. And here, just for the pleasure, showing pictures coming from the recent flybys of the 3 of the Galilean moons by Juno. So you have Ganymede to the upper left side, which will be the main target, of course, and even a destination of JUICE. You have here Io in 2 different views, and you have Europa. So Callisto is missing, but don't worry, JUICE will do a great job at going to Callisto, and probably also after that, the Chinese mission to Jupiter, Tianwen 4. So let me go now to what the moons are doing in terms of interaction. So let's think first about the tidal interactions. I have borrowed the next 2 slides to Valérie Lenné, who is sort of my teacher on that. Of course, it's not my field. Well, there is a general law, let's say, that when you have a moon which is orbiting a planet, you have to understand its motion as a function of its position with respect to the synchronous orbit. So let's take a moon which is inside the synchronous orbit of its planet, like, for instance, Phobos at Mars. So in that case, when the moon is orbiting, it is raising on the planet a tidal bulge, which is lagging behind the moon. And the result is that the tiny differential force that is acting on the moon is actually decelerating the moon on its orbit and taking energy, well, very small energy, of course, but taking energy from the moon and dragging it towards the planet. If you take, on the other hand, a moon which is outside the synchronous orbit, and that's the case of our moon, of course, well, in that case, the tidal bulge, which is generated by the moon on the planet, on our Earth in that case, is actually accelerating the moon along its orbit and pushing it outwards. As we know, our moon is moving away from our Earth by about 3 or 4 centimeters per year. So that's very significant, and that will never stop. So in these systems, in the case of a single moon interacting with a single planet, we have a very simple scheme in which the tidal interactions and the dissipation of energy between by the tides inside the planet and inside the moon produce a steady motion of the moon towards the planet or away from the planet. So that's something, of course, very important to understand. And what is also interesting to understand that, in fact, this is not the case at Jupiter. At Jupiter, we have a different situation. And the reason for this different situation is what we call the Laplace resonance. So it is the 1-2-4 resonance in mean motions between Ganymede, Europa, and Io, by which when Ganymede does 1 orbit, Europa does exactly 2 orbits, and Io does 4 orbits, and the phases of the orbits remain stable as written in this equation here. And the reason, the consequence of that is that instead of going away into the system or going towards Jupiter, as expected for a single moon, the system made of Io, Europa, and Ganymede is in an oscillatory motion and remains trapped. So the configuration of these 3 moons remains stable. So that's a process that was studied by Pierre-Simon Laplace a long time ago, I mean, end of the 18th century, hence the name, of course. And he actually showed that the motion, the evolution of the motion of the moons is something like an oscillatory motion in a potential when we have a mechanical system in which the three objects are actually linked and trapped. And so they don't move away, but each of them is drifting. And just as in the case of a single moon, the drift frequency or the drift speed is a function of the famous K/2 coefficient, which is the coefficient by which describes the amount of dissipation of the motion of the moons into the interiors of Jupiter and of the moons themselves. So that's a really very important process by which energy through the tidal interactions is actually transferred from Jupiter to the three icy moons, so the three moons on the Laplace resonance. And here, of course, most of the energy, and that's a key point I wanted to make, is going into the heating of the interior of Io. Why heating? Because on this Laplace resonance, each of the moons is maintained on a slightly elliptical orbit, so that it is actually moving into and out as a function of distance to Jupiter. And in this slight radial motion, the moon is squeezed by the jovian magnetic field periodically, and this squeezing produces the heating of the interior. So the consequence of that, of course, we know it's very spectacular. It is the volcanism of Io. And here I wanted to show some results relatively recent from after the Io flybys of last year with Juno, where in particular the GERAM team with Alessandro Morin leading the effort was able to make discovery of the way volcanism is organized at the surface. And the GERAM team found actually a series of lava lakes, so very interesting structure. You have here actually the temperature, let's say, measured by GERAM in that case. You see that there is an annulus of heat which seems to correspond to lava, which is actually a liquid at the surface, and at the center there is a cooler part of the lake where the lava is solidifying. So these lava lakes have been characterized by GERAM, and it so happens that they are a very important feature in the way Io is actually sending energy outside. So you see here another nice view of Io's volcanoes. Many of these features correspond to lava flows, and we know now that most of the heat coming out of Io is not evenly distributed over the surface, but really is concentrated through the infrared radiation of these hotspots at the surface. So you can understand that, of course, this makes this process of Io cooling very complicated, but it is also related with the generation of the atmosphere of Io by volcanism, and therefore to the rest of the story I'm continuing to tell you now. So the rest of the story, well, is that Io is generating via the volcanism a neutral torus. The neutral torus is basically distributed along Io's orbit, but it is ionized very quickly under the effect of a bombardment by the electrons of the magnetosphere of Jupiter, creates a plasma. The plasma, of course, does not go along Io's orbit. It goes along, let's say, the centrifugal equator of the magnetic field into which it is trapped. So it is generating a plasma torus, which is slightly displaced in inclination with respect to the orbit of Io, going up and down, as you see. So this Io torus, as the rest of the story tells, is going all around Jupiter. And via a centrifugal effect, I mean, the plasma is pushed outwards by the centrifugal force. it generates what is called the magnetodisk. And the magnetodisk is itself, after that, interacting with the other moons. So let me say a little bit about these interactions between let's say, the plasma, the magnetodisk, and the moons. The best template, of course, is EO. It's probably the best documented one. We know for a long time ago already that, well, with the Galileo studies, that the planet-moon magnetodisk interactions are basically described as the interactions of a moving plasma, which is the plasma of Jupiter, with an object, which is here, in that case, EO. In this interaction, well, the disturbance produced by the flow of the magnetoplasma by a moving object here generates two Alfvén wings, and the Alfvén wings are propagating along the direction of magnetic field, and their direction is the composition between the relative motion of the moon with respect to the magnetoplasma and the Alfvén spin of the motion of the wings along the jovian magnetic field. So these Alfvén wings, they are really the key product of the interaction. But let's go to the next steps. Well, we know they propagate outside, away from Jupiter. They are refracted at the edges of the plasma sheet here that we call also magnetodisk. They go down to the ionospheres of Jupiter on the two sides. And you see the complexity of the process is that there are multiple bounces of the Alfvén wings generated at the interaction of EO with the magnetoplasma. And what we see is actually the effects of this multiple bouncing of the Alfvén wings bouncing on the northern and southern ionosphere of Jupiter. So basically, Juno has been investigating the details of this interaction. And here, Bertrand Bonfont actually had a cartoon before the arrival at Jupiter, which happens to be basically correct. And it's formed in particular by observations of the generation of aurora by the EO interaction. So the idea here, you see, you have the plasma torus here. You have Jupiter in the back. And imagine that this in blue is an Alfvén wing propagating. So you see it's going, starting from EO here. Assume here that EO is near the northern edge of the plasma torus. It is going to the northern Jovian ionosphere, making a reflection, coming back, refraction through the plasma torus, then going to the southern ionosphere, and back again. So in blue, you have the first type of interaction, which is the generation, let's say, of the motion, refraction, and reflection of Alfvén waves from the obstacle that has generated them to the two mirrors, which are the northern and southern ionospheres. But in addition to that, it was discovered that each of the interaction at the reflection on the ionosphere of these Alfvén wings also generates directed acceleration of electrons. And these electron beams in red, we see them here. So we see electron beams which are conjugate to the place where an Alfvén wave has been reflected. So we have a system that you can see in the aurora, where you have points where you see the reflections, and you also have points where you see electron beams going from one hemisphere to the other. So of course, it's quite a complex system. And if you look at the other hemisphere, you will see the opposite picture. The Alfvén wave is reflected first on the south, then goes to the north, and each time it is generating an Alfvén beam, an electron beam at the reflection. So basically, this has been studied in great detail by the observations of Juno. And here you have images taken with the GRAM camera again, where you see a very interesting structure of the tails of the moons generated by their interactions with the magnetoplasma at Jupiter. So there are sort of projections of the interaction on the ionosphere of Jupiter. And you can see the whole family of interactions, Io here to the left, Europa at the center, and Ganymede at the right. All these are satellite footprints that you can see in the infrared, and you can also see in the UV with the UVS camera. So they tell us a lot of things about this very interesting interaction. And I wanted to say one more thing, which is that, well, in the case of Juno, we are actually flying close to the ionosphere of Juno. And one of the interesting things is that because of that, we see not really the place where the interaction takes place near the moon, but the effects of the interaction away from the moon and near Jupiter. And here, this is a study that was done by Jonas Labia at IRAP, a PhD student, who really looked into the details of the electron acceleration at the different moons, Io, Europa, and Ganymede, taking the observations by the electron sensor of JADE, so the thermal plasma. And he was able to show how by studying the precipitating electric flux, the mean energy, the energy distribution, you can really start to understand how the electron acceleration on the magnetoplasma is produced by the effect of the interaction between the moons, each moon and the magnetosphere. And I wanted to say here, this study is going to be very complementary to what JUICE is going to do, because JUICE is not going to fly very close to Jupiter, so to the feet of the flux tubes of the moons like we do here. But JUICE is going to study in great detail what happens near the moon. So in a way, we are starting to understand a fraction of the story and prepare for the broader story that JUICE is going to tell to us once you are at Jupiter. So next step, well, of course, I was showing something which is sort of a detail of the interaction of each of the moons with the motion of the magnetoplasma. If we go to the bigger scale now, what we have here is the structure of what we call the magnetodisk. And here you have Io, which is the main source of plasma, as I said. We know that by centrifugal effect, the plasma generated at Io is transported outwards up to the regions where it is actually interacting with the solar wind. As I said, it is interacting with each of the moons. Well, this magnetoplasma here becomes a giant magnetodisk, which is rotating with Jupiter. And here, another type of interaction, which is very important and interesting, is how this magnetoplasma disk is actually maintained or dragged into rotation with Jupiter. And the way it is done is via electrodynamic coupling. So we have here a disk, let's say a conducting disk, which is rotating. In the disk, you have the possibility of current circuit. And the current circuit, in particular the radial currents, which are flowing here, are actually closing along phi lines into the jovian ionosphere. And as you can imagine, the Laplace force, which is acting at the two ends of this giant electric circuit, here in the magnetodisk and here in the ionosphere, actually the two conjugate ionospheres, works in such a way that angular momentum is taken away from Jupiter and transported into the disk to keep, at least partly, its co-rotation. So this theory of the co-exchange enforcement was developed by Tom Hill a long time ago and really put into a mature theory by the Leicester group, so Stan Cowley and Emma Bulls, a very famous model, which we are now, of course, revisiting, reconsidering with Juno, but which remains an important guideline on understanding this global transport and coupling between the disk and Jupiter. To finish the story, well, what happens here is very important, and the current circuit, as we see, is closing through the ionosphere. And if you go through the upper atmosphere now in more detail, what happens is as the current is closing through the ionosphere, of course, there is particle precipitation, there is joule heating here. So energy is deposited in this interaction, and it is deposited in the upper atmosphere of Jupiter. And of course, the thermosphere is not a passive medium. So the end of the story is that the joule heating, which is deposited into the upper atmosphere of Jupiter, is going to drive the thermosphere itself into a large-scale transport, large-scale circulation. And there is some redistribution of angular momentum energy between the latitudes of the old zones where energy is deposited to the higher latitudes in the pole, and also, more importantly, toward the lower latitudes. So basically, this is the end of the story, and I would like now to wrap up. Essentially, we have gone through all this system here, saying that the energy is coming from Jupiter. Magnetic field creates the magnetosphere. Tidal motions are generating heat inside the moons. Heat inside the moons is generating plasma and the magnetodisk, and the magnetodisk is coupled back to Jupiter via electrodynamic interactions. So our dream, of course, in this study is to really understand this system quantitatively. We need to measure the fluxes of mass, momentum, and energy through the system. And I'm sure that's something that we started with Juno, but which will really become possible with JUICE once we are in JUICE orbit. So to summarize, there are many key questions that we have about the flow of mass, angular momentum, and energy through the Jupiter system and the associated mechanism and timescales. Here, I just summarize a question first about the long-term evolution of the system. How does the jovian magnetic field change with time? Which, we see it is changing over just years and decades. So what happens over millennia, over millions of years and billions of years? What are the dominant tidal modes that couple the interior of Jupiter with the moons? Let me say that we don't know. This is a really important question, being able to determine what are the dominant tidal modes. And it's a big question mark. And of course, what are the consequences on the orbital evolution of the tidal heating of the moons? Another important question mark that I think JUICE will be able to address. Then now the transfer mechanisms and timescales. Well, we have many questions. How important is vertical transfer of momentum, in particular in the jovian atmosphere? It's critical in the way the atmosphere is driven by the interior and drives the magnetosphere. How does the transfer work through the EO system? We see it's very complicated. There are internal heating, volcanism, and then generation of the neutral atmosphere, and then the plasma torus. Coupling the plasma torus to the disk, radial transport and plasma heating in the disk, transfer between magnetodisk, moon, Jupiter, and interplanetary space, and redistribution between latitudes in the thermosphere. But of course, it's not the end of the story, because the other theme of JUICE, in fact, is the question of habitability of the moons. And I will say a few words now about the connections. In fact, there is important implications from the workings of the Jupiter system on habitability. And to make it short, well, liquid water is maintained by the fact that the interiors of the moon are heated. Part of the energy also comes from tidal heating, and part of the chemistry, I mean the chemical elements which may drive the biochemical reactions inside the putative oceans of the moon, is also related to the question of the transport processes in the system. Martin, where am I in terms of time?
Yeah, it's close to the 1 hour, but you can
Okay.
have a couple of more minutes to finish, so that would be great. Okay. Thank you.
So just go quickly about the implications on habitability. Let's say that we have many questions on this connection between the two themes of Jupiter, of JUICE. Implication on habitability of the way the Jupiter system works. For that, we need to understand what is the importance of the potential exogenic contribution to the icy moon's habitability. How much tidal heating of the internal oceans is taking place? We need to have quantitative figures. How much transport of heavy ions coming from Io, for instance, goes to the icy moons and to their surfaces in particular? How much does the bombardment of the surfaces of the icy moons produce oxidants that may actually reach the oceans? And how do these factors change over time? Because, of course, a key element in this process is time. If we want to understand really the habitability of the moons, we need to understand for how long such things as the existence of liquid water, the existence of nutrients inside the moon, the existence of energy has been taking place. So with that, I think we have a lot of work to do with JUICE. And of course, I am extremely happy that the mission is going so well now, and we look forward to a fantastic time when JUICE will be in orbit. So I will stop there and be very happy to address questions, of course. Thank you very much.
Thank you so much, Michel. Thank you so much, Olivier, for your wonderful talks. I apologize for the sudden sound that you might hear in the background. There's apparently some work going on here nearby. Questions, and there's already one question in the chat. Randy Gladstone, he asks, do you think Europa plumes exist, and would they contribute anything to the plasma disk?
Yes, well, thank you, Randy, for the question. I don't think Europa plume's existence has been confirmed, as far as I know. But I would say, if they are, for me, I think the most important value is that there would be a sort of a proof of the fact that Europa is an active body. I mean, you know how important was the discovery of the giant plumes of Enceladus. In fact, it made Enceladus sort of the most compelling object for the search for a habitable world in the outer solar system. So I would love to see those plumes. And of course, if they exist, one, they tell us something about the fact that the ocean interacts and exchanges material with the surface, so that's a key element. And second, because of the radial motion and transport in the disk, yes, there would be a source of, water constituents for the moons which are farther away, in particular Ganymede and Callisto. So that would be a major element.
Okay, thank you. Another question from Pascal Renier. Do you confirm that Taiwan 4 will include a lander on Callisto? I guess you might be better placed for that.
Sure. Well, thank you, Pascal. We discussed this question many times, and I would be very happy to confirm, but I cannot because the Europlanet 4 mission is still under study. I think I can say our Chinese colleagues are considering very seriously the option, but they have not yet made a firm decision. So we have to wait until the mission moves to the implementation phase with an official announcement. And at this time, I think we will know the mission scenario. So let's be patient and wait maybe a few moments.
What is the timeline for this mission at the moment?
Well, from what I know, if it is announced like expected, I think by the end of this year or maybe early next year, it could be launched around, I heard 29 or 30, something like that, and which would put it to Jupiter by the second half of the 2030s. So a very good time to sort of continue the work after JUICE and make a continuous survey of the Jupiter system. It's one of my dreams, of course, that this timing would work so well.
Okay, thank you. There is another question. Sehapal Singh, I hope I pronounced that correctly, asks, tidal heating contributes to active volcanoes on Io and potential liquid ocean water beneath Europa. Is this difference only due to composition of the two inner moons? Does tidal heating offer any similar kind of significant effect on Ganymede or the other outer moons?
Well, I think the key element is that the distribution of heat between the three moons is not comparable. So most of the energy, I don't know the figures, I don't remember, but most of the energy goes to Io, in fact. And so the effect of tidal heating is lower on Europa and still lower on Ganymede. So there is a decrease in the interaction. And that's the reason why Io is the most spectacular receiver, let's say, of tidal heating. Then, of course, tidal heating doesn't have the same effect depending on whether you have water or not. Io is a dry body. It's a fire body. It's the most volcanic body in the solar system. And Europa and Ganymede have water. So for this reason, of course, the way tidal heating is deposited doesn't have the same effect. In fact, we don't know, I think, very well how is tidal heating distributed for Europa and Ganymede between the ice and mantle and the oceans. So that's something which is an open question. But for Io, there is really much progress on the fact that we know much better now with all the effects of the heating.
Thank you, Michel. I hope it answers the question. I guess Io, if it had any water, it's just gone by now.
Yes, actually, I think it's an open question as well. Was Io originally without water, or did it lose seawater? So I think there are models of the two types which exist. Some models just say, oh, there is a chemical gradient in the formation of the moon. So it means it points to a chemical gradient in the primordial circumplanetary disk. And some other models don't have this gradient, but say, well, Io lost its water because it receives most of the heat.
There's an additional question by Mauro Pirarba. I guess it's for Olivier. How will JUICE and Europa Clipper observations complement each other?
Yes, that's a very good question. So there are different levels of answers. First, in terms of science goal, Europa Clipper is really focused on Europa. And JUICE, there will be only 2 flybys of Europa, so it will not be the focus on the mission, and will focus on Ganymede, Callisto, and the rest of the system. So in terms of science goal, there will also a good complement with a very little overlap with the Europa science. But in addition, there will be a lot of opportunities to work together. For example, for Europa, if we take the example of Europa, there will be flybys by Clipper, many flybys, and 2 flybys from JUICE. And here, the observation from the 2 spacecraft will be very interesting to put together, because we expect to have great, fantastic new discoveries. And it's always better to confirm these discoveries with 2 sets of independent observations. And the payload on both spacecraft is a little bit different, but relatively similar. So it's already one kind of complementary. It's always good to observe also the similar, for example, the surface with different illumination conditions, different time, because there is some variability in the surface, in the atmosphere. So it's good to have multiple observations. And also a very interesting complementary set of observation is that it's the multi-point observation, the 2-point observation in the Jupiter system, because the spacecraft will be always somewhere. So we can have an example of one spacecraft close to a moon, and another spacecraft somewhere else in the magnetosphere of Jupiter. And we can really compare the 2 observations and deduce very useful information on these couplings, as outlined by Michel. For example, what happens at the moon, while the other spacecraft sees something else further away, or the other spacecraft observe Jupiter, the array of Jupiter, while one spacecraft observes the local plasma environment. So there are a lot of of complementaries. It's a very rich field of investigation that we are preparing.
Yes, excellent. Thank you very much. Okay, we have gone a little bit over the hour. I don't see any further questions here in the chat. So I think it's a good moment to stop this webinar. And with that, I would like to thank again very much Michel and Olivier for being here. Everybody who attended, thank you so much for listening and for asking your questions. And we'll be back with a new webinar in about 2 months' time. So have a great rest of your day and see you at a later moment.
Thank you very much.
Thank you.
Bye-bye.
See you soon. Bye.
Bye-bye. Bye-bye, everyone. Bye-bye.